Hi, my name is Stefan Borsky and I'm presenting a joint work together with Alexander Mabler. We're both from the University of Graz. And so I have the comfortable position that actually my paper was very well motivated in the first keynote today in the morning, which was more or less about urbanization and climate change. And this is actually what we're also doing in this paper. And the basic idea is what we want to do is we want to estimate the dose response function of climate change caused agricultural productivity shocks on city growth in Sub-Saharan Africa. So, wait a second. No, oh yeah. So, what was also told today in the morning is, cities are growing worldwide, and today around 55% of the human population live in urban areas. And the most growth actually happened in Sub-Saharan Africa in the last 6 decades. And still, when you look at this region, there's still around 57% of African population which lives in rural areas. So there's a lot of potential of people which could move to cities. So what we also have seen today in the morning session is more or less that the classic factors of urbanization has changed. Historically, it was based on economic development and structural change, and this is something different now. When you look at cities in Sub-Saharan Africa and low and middle income countries, they urbanize faster and in a much earlier stage of development. Now we have seen this one line of Sub-Saharan African urbanization rates and economic development. It was very stable economic development and an increase in urbanization. And so in some way, this put the question forward, so maybe the drivers have changed, and there is more and more literature showing that there are pull and push factors which drag people from rural areas into urban areas, and what drives urbanization in these regions. And with climate change and with an increase of these weather-related push factors, urban growth will also increase in future. So, based on this setting, so our aim of this study is more or less to estimate a dose response function of shocks in rural water availability on the effects of nearby city growth and in Sub-Saharan Africa. And what we do is actually we allow for nonlinearities in our response function of city level growth, which is a little bit different to the existing literature. What we also do is, what is also motivated in the morning, is we differentiate between city size. So we differentiate between small, medium and large sized cities. And then we apply state-of-the-art methods to identify cities worldwide in Sub-Saharan Africa, and we use more or less the latest hyperlocal remote sensing and climate data. So why do we care? Why is this important? Now, to address city growth or to address urbanization, you need to know its causal regions. And especially in these regions where growth is happening very quickly, you need to understand, okay, what drives this growth to do something against it, how to work with it. And the same is true also as a decision maker. If you need to understand the direct and indirect responses of adaptation measures, for example, against droughts, and this can also lead to changes in city growth. And now, because of climate change, these disturbances in water availability become more frequent, longer in intensity due to climate change. So, due to the fact that we work in a region which is actually data scarce, we have to rely on a large set of remote sensing data to do our study. And what I will do now is I will guide you through our data generating procedure in some way to convince you that we're able to measure, first of all, cities in Sub-Saharan Africa and also agricultural relevant productivity shocks. So what we do is more or less, we start with population grids. So we work on a grid level with 1 kilometer grid size. And so the first step what we need to do is we want to identify the city core of a city. And so what we do is we take gridded population data and build up area and identify grids, consecutive grids, which form a cluster and which is the core. Okay, so each grid cell in this core has a population density which is above 1,500 people per square kilometer and a build up area which is above 50%. When we have defined this grid, this core, in the next step, we identify the fringe which is attached to this core. Okay, the fringe are all grid cells which have at least 300 people per square kilometer density and are in 60 minutes commuting time to the core. Okay, so with this we get a city hull. So this is the city hull of Nairobi, which consists of the core and the fringe. So then we have the city hull, and then to estimate or identify year-to-year changes in city growth, we use the newest set of nighttime light data, which is called black marble data from NASA, which estimates or which identifies changes in luminosity at a very, very small scale level. So it's especially suited to identify changes in economic activity at highly population dense areas. And so by this we can measure the change in economic activity from year to year in this hull. And so now we have defined the city boundary, and now we have to attach the relevant rural area to the city boundary. So what we do is so there's Nairobi is in the middle, and so what we do is we draw a 300 kilometer times 300 kilometer box around this city, and for each cell in this box, we identify first is there agricultural production or not. So if there is agricultural production, we take it. If not, we don't take it. And then we identify the growing season of each cell using satellite information. More or less, we look at the level of the degree of greenness in this cell and see, okay, from the month with the highest level of greenness, we calculate the growing season in the cell. And then, based on this growing season information and agricultural production information of the cell, we look at, okay, so how much water is available relative to a long-term mean. Okay, so does this cell has a water availability shock or not? And by this, in some way, we get a shock in production, which is agriculturally based, more or less, so agricultural relevant water shock, and which is around the city. So to bring these shocks to the city level, we put on this, we put a friction surface, which is like information, how long does it take to go from one grid cell to the city. So it takes information from all type of transports. Now if you walk on a paved road or on a dust road, or you have to cross a border and so on and so forth. And it gives you more or less the minutes from each grid cell to the city. Okay, and so by this we weight each shock, we weight by the amount of time until it gets to the city. So by this, in some way, we are able to estimate the spatial equilibrium. And and we do this, and at the end, our sample consists of 2,376 cities in Sub-Saharan Africa, and we differentiate the cities between small, medium, and large-sized cities. So all cities which are above 1 million people are large-sized. All cities which are between 1 million and 50,000 are medium, and then all cities below 50,000 are small cities. In some way to differentiate the role cities play in an urban hierarchy. No? So it's or in a spatial hierarchy, because small cities attract people differently than large cities. And so using this data set, and we have this for 10 years, so from 2012 to 2021. And so what we do just very quickly is we estimate a dose response function where we have first and second order polynomials of the oh, that's difficult. I don't know how this works. Of this rural water availability shock, and we also control for city weather events, which maybe confound our estimates, and we have city and time year fixed effects and trends. And so our identification is more or less based on this random natural variation, precipitation, and evapotranspiration, a source of exogenous year-by-year realization of water availability shocks during the growing season outside of cities. And so when we do this, we estimate like this type of functional form. And so what you see is, on the x-axis is more or less the standard deviation, the strength of the shock measured in standard deviations. So on the left, so when it's get negative, it's a drought shock. When it's get positive, it's a water shock, it's a wet shock. And so what you see is you see this U-shaped curve, more or less. So when you have a drought shock in the rural areas around the city starts to grow by, for example, 2 standard deviation shock leads to around a 6% growth of the city. When it starts to get wetter, then you have favorable conditions. So between 0 and 1.5, actually, that's favorable conditions for agricultural production, so you can produce more than normal. You have actually cities are decreasing slightly, and then you see the curve again start to point upwards again when you have a stronger shock. I'm nearly done. So then we were asking ourselves, okay, so are cities differently? So here, what you see here is you see the growth paths of our cities measured in nighttime light over our time period. And so the red line is small cities, the black line is medium-sized cities, and the blue line is large cities. And so what you see is that all of them grow tremendously. Now, in these 10 years, they grow between 25 and 35%, which is a lot. And but what you see is, for example, that larger cities grew by 35%, and small and medium-sized cities by around 25%. So we're asking, so do they react differently? So do they receive different, or do people react different in the migration decision depending if they're close to a small city or close to a larger city? And so when we do this, then you see here on the left-hand side, it's large cities, then in the middle is medium cities, and the right-hand side, large cities, medium, and the red is the small cities. And what you see is I'm nearly done. What you see is for large and medium size, you see this U-shaped curve, but actually for small cities, you see, again, they grow when they have a drought shock, but actually when they have a wet shock, people start to move. And so this is more or less the status where we are, where we start exploring it, and there are papers showing that actually it depends on the skill set of people to which cities they more or less move. And there's papers showing that in case of wet shocks, high-skilled people start to move, and they're more likely to move to larger cities than to smaller cities. And that's all, more or less. So what we have done is we have shown that disturbances in water availability in agricultural production create this growth of cities nearby. And so what we'll do next step is we will work strong on this heterogeneous between cities and then also within cities. So we want to understand, are people moving to the fringe, or are people moving to the core? That's all. Thank you very much.
Okay, thank you so much.